Thank you, Jean. How's it going with the polls? Matthias, do we have the results?
Yes. Here we go.
Yeah. Oh, wonderful. Oh, so some of us are already starting to fish for tuna. So tuna is establishing systems practice in your organization. Many are fishing also for octopus, so adding a systems perspective to our projects. So there are also lots of sardines fishermen. So this is to be part of a community of systems practice. And Barracuda explaining exploring the concept of systems practice and other. I would love to know the other, so it would be great for those that have written other to just type in what are you fishing today. This is quite different from last time. Last time it was mainly Barracuda, so I'm glad you have persisted to be fishermen and continue to fishing sustainably. So 78% have joined the previous dialogue, which is great, and 22 are new. So Jean, thank you for having presented yourself. And can you share with us some of the takeaways from the last workshop? Next slide, Matthias.
Yes, so for those of you who joined the last workshop, this is a small repetition, and for the others, just like a small introduction of what we looked at in the workshop a month ago. So first of all, we looked how interventions in complex systems can actually lead to unintended consequences, for example, at the Kiribati case. We introduced system practice as a way to understand system behavior and to develop better interventions for the long-term health of the system. We also introduced how systems practice can sharpen your skills in holistic thinking, your ability to work collectively, and also improve your analytical skills. And finally, we concluded that becoming system thinker is a journey, and it requires some time and also experience through practice to reach that level. And there's also a link to the recording for the ones of you who couldn't join a month ago, which you will find in the slides, and I think also in the invitation from Matthias. So Malika, what's on the agenda for today?
Thank you. Very exciting, our agenda. Next slide, Matthias. So today, our learning outcomes, we will be exploring how system practice is invaluable for systemic theory of change. And we will be doing so by exploring through youth theory and practice. And we will be asking you lots of questions. So pay attention when we're explaining different concepts, because when we get to the example, we will be asking you, we will be seeing how you're following the concepts through a very nice example that we started last week. So for the learning outcomes, we will be understanding patterns, so looking at behaviors in the systems. And for that, we will be going a little bit deeper in theory. We will be theorizing change, so we will be applying the Brazil case again to develop a systemic theory of change. We will be looking at leadership through complexity. What kind of emotions do you see through different behaviors in the systems? So bring not only the system structure and system behaviors, but the human response often to that complexity. And lastly, we hope we will have time. We will see what you think about different COVID policies, and we'll be using system modeling to test different policies. So let's crack on. Next slide. So Jean, tell us more about systems thinking.
Yes, thank you, Malika. So the first part is about how we can understand patterns. So everywhere in the world, when we look at developments, we can see different behavior patterns. I'm sure by now most of you have seen those two curves in relation to the COVID epidemics and to the flatten the curve. And that's actually one goal of system thinking. We want to try to understand what are the systemic causes that kind of lead to this pattern, and then to see what can we do to influence those patterns eventually. And we want to start with a little experiment, with a little game on the next slide. And so the experiment is called paper fold, and I would like to ask you, if available, to take like a small A4 paper or a napkin or something similar that you can easily fold several times. So I have mine here. Great. See already some papers. And no worries, if you don't have a paper or something, also no problem. It's also okay to watch what we're doing, and I'm gonna do it here for you as well. So, and then on the next slide, if you all have your papers ready, very simple, would like to ask you to fold it in half 4 times. So like 1, and fold it, and then a second time in the middle, always folding it in the middle. And I have 3 and 4. So kind of this is now how my paper looks like. I see you all folding, very nice. Great, and so if I look at my paper, and I guess yours similarly, so you see that the width is kind of, it increased. And mine looks more or less like 1 centimeter. So the height, the width of the paper now. And if we go on the next slide, Matthias, the question is now, okay, assuming this is 1 centimeter, and imagine now you could fold this little piece of paper in half 29 more times. So what would you think, how thick would it get? So take a second, think about it. You can also play with the paper a little bit if it helps. And of course, you could also calculate it. Here it's more about intuition, like what you think. And we also, if you go to the next slide, Matthias, give you some options that you can choose from. So if you could fold it 29 more times, what do you think, how thick would it be? Like as high as a basketball player, as high as a single-story house, and so on and so on. So yeah, if Matthias starts the poll, you can all choose something. So Matthias, you can tell us as soon as everyone polled.
Yes, I will.
Let's see how good the mathematical skills. Oh no, you said intuition.
Okay, the results are in. And so I see 35% basketball player. We have also some people, 20% redwood tree, 20% Kilimanjaro. Oh, and 5% also say once around the world. Very interesting. So we have all the answers there. Thanks for polling. And yeah, now let's see what is the answer. If we go to the next slide. It is actually the second to last answer. So it's a distance from Europe to the US, or actually to be exact, it's a distance from Lisbon to New York approximately. It's like if you fold it 29 more times, it's actually going to be around 5,300 kilometers. And this can be quite surprising. It's always surprising to me when I do this experiment because it's quite simple. Our human minds are not really made to think in such exponential terms. We're really good in addition, we're really good in multiplication, but exponential growth is much harder to grasp for our minds. And if we go on the next slide, there we can actually see how quickly this grows exponentially. And so here we see the doublings of 1, and on the bottom on the x-axis you see how many times we doubled it. And you can see if it starts at 1, after 29 doublings, it's about 500 million already, which would translate to our 5,000 kilometers. And if we would continue, make it 33 times, then we would get to 9 billion. So this can kind of escalate quickly when we talk about exponential growth. And that's why it's so important, especially if you want to understand systems that show exponential growth and want to handle it, that we have tools to do that. And on the next slide, that's why we use systems thinking. So as a quick repetition and summary from the last workshop, system thinking is the art and science of making reliable conclusions about the behavior of a system by developing a deep understanding of the underlying structure and mental models. And a nice figure to explain this is the iceberg on the right. So on the surface, we have the events quite visible. What's more interesting for us from a systemic perspective are the patterns. So what kind of behavior do we see over time? For example, this exponential growth. Then we want to understand what are the causal reasons. What is the underlying structure that can explain the pattern that we see. And finally, we also want to understand the mental models, the values and beliefs of the actors that's driving and sustaining those structures. And if we go on the next slide, so here we can now see what is the structure behind this little experiment that we just did. And basically what we have there is called a reinforcing feedback loop. And that is a closed sequence of causal effects that's reinforcing some kind of initial development. And here on the left, you see kind of the main variables. So we started with a certain height of the paper, and the higher the paper, the more amount we add with each of the folding. And with each amount adding to it, we increase the total height of the paper. So this is like a reinforcing loop. And if we only have this reinforcing loop in place, you see the behavior on the right. It's going to be an exponential growth and going up forever. And this is also where we say structure, so the causal structure of the system drives its behavior that we can observe. And here also a quick question for you. So if you now see this exponential growth curve and this reinforcing feedback, where else, what other examples do you know? Where else do you see kind of such a behavior, or where else do you see reinforcing feedback in systems? You can take a second to think about it, and then I would like to ask you in the chat box to kind of share your insights. Anything coming to mind if you think about exponential growth? I see. Pandemics and technology, yes, very nice. And thanks for the reminder, Matthias. Of course, also feel free to share your comments in Spanish in the chat box, and then we can translate them internally. We have also Simon, compound interest in finance. Yes. Very true. That's how kind of the bank account can grow in the best case. Climate change, yes, kind of the long-term reinforcing loops that we can see there. Fake news, human population growth, yes. Nice, great. Thanks for sharing. Advertising, consumerism, exactly. So if we go on the next slides, these were also the ones that you mentioned. Some examples from our side. So as someone said, pandemics, absolutely. On the left, we see kind of the infection reinforcing loop. So the more infected people we have, the more contacts there are with infected people, the more susceptible people get exposed to the virus, the more infections we have and the more infected people we have. So this is reinforcing loop. Someone also said population growth. That's also exactly right. The higher the birth rate, the higher the population, higher the birth rate. And one other example is also the poverty trap that we can see, that the higher the poverty level, the lower the access to education, the lower the opportunities on the labor market, and the higher the poverty level. So this is then not something that grows exponentially, but this is kind of trapped within the poverty line. And so if we go on the next slide, Matthias, just quickly, as you've seen in those little system maps that I showed, you see those polarities, those pluses and minuses. And just as a little input, those describe the direction of the relationship between the elements. So if it's a plus, it doesn't necessarily mean that it always grows, but the plus means that both elements move into the same direction. So if birth rate increases, population increases. If birth rate decreases, population also decreases. So they move into the same direction. And the opposite for the negative polarity. So if you see a minus on this link, this means the two elements move into opposite directions. That means if death rate, for example, increases, then population would decrease. And if death rate decreases, population would increase over time. Just for you as a little side note. And now I would quickly ask you to take back your papers. And so if we now know, okay, 29 more times and we could cross the Atlantic with the paper, then maybe let's try it. And let's just try to fold it 29 times and see how far we get. So I can fold it one more time at 5. Now I'm at 6. And yeah, at least for me, it stops after 6. I don't know if some of you get any further. And that also symbolizes a very nice lesson of system thinking. Nothing can grow forever. If we look at the next slide. So there's always some kind of limit to growth. And in this case, it's actually a balancing feedback loop. And formally, it's defined as a closed sequence that drives a system behavior towards a goal or a limiting condition. And on the left, you see now the example of the paper fold. So we have this reinforcing loop, but the higher, the wider the paper gets, the more stiffer it gets, and the less we can fold it, and the less amount we can add. So this is actually a balancing loop that limits how much the system can grow. And that means we don't really have an exponential growth, but we have this S-shaped growth. So in the beginning exponential, but then as we are approaching the limits, it's flattening the curve. And on the next slide, we see also that the other examples that I told you, that I showed you before, also have these kind of limits in place. So for example, for the infection on the left, there's only a limited number of population. And with each new infection, there's less susceptible people. So there's less susceptible people exposed to the virus. So it's also going to be like this S-shaped development. The same for the population, as we have a balancing loop with a death rate, maybe depending, for example, on food availability. And also for the poverty trap. Hopefully we have financial resources available that we can invest into educational institutions and therefore ease the access and improve the access to education for everyone. And if we go to the next slide, there is a second, so much to the feedbacks. There's a second very important concept if we want to try to understand behavior we see in the real world, which are delays. Because not every of these causal effects that I showed you before is immediate. Sometimes it takes some time. Sometimes the effects are delayed. And a very nice example here is also now with the COVID, the timeline of an infection. Maybe a patient is infected on day 1, but it takes 3 days until the patient shows symptoms. Might take another 2 days until he's tested. Might take another 4 days before the test results are available. Another day until the test results are reported up the hierarchical chain, and maybe 3 more days until the patient is informed. And delays are not inherently bad within a system. They also keep it stable, but we need to consider them when we try to understand it, and especially when we try to intervene. So here, for example, it's important to know that even before the patient shows symptoms, he might be infectious. And we need to consider that when we want to understand what's happening. And if we intervene and base our decisions on the results on day 11, we also need to consider that these results are already 11 days old, and they more represent the situation 11 days ago. And there's a nice quote that kind of summarizes this, that the right decision is the wrong decision if it's made too late. And that's why it's important to consider those delays. And if we look at the next slides, we can actually see how huge the impact of delays can be on the system behavior. So here we have the population example from before. And in this case, the population, though, creates pollution. And this pollution over some delay, this is why kind of these two lines, the pollution with the delay impacts the food availability. It actually decreases the food availability, which then determines the death rate. And on the next slides, we can see how different times of the delay can lead to different behavior. So the first example, we have like a small delay. So we might have exponential growth, and then it slowly flattens and the population might stay at a high equilibrium level. If it's a medium delay, we see there might be oscillations that destabilize the system. And in the worst case, if we have long delay, then it could lead to an overshoot and collapse, as we can see at the very bottom. So it's important to consider delays when we talk about the behavior. And on the next slide, Matthias. So in summary, in system thinking, we kind of talk about those 6 behavior modes that can relatively well describe all behaviors that we see within systems. So we can have exponential growth, goal-seeking behavior, S-shaped growth, oscillation, growth with overshoot, or the overshoot and collapse. And on the next slides, and as we just showed before, each of them can be explained through feedback loops and delays. So the reinforcing loop leads to exponential growth. And at the bottom right, overshoot and collapse is basically a reinforcing loop, and the balancing loop and the long delay. And the fascinating thing is that almost every system behavior in the world can be explained by those behavior modes. It's mostly not as pure and as simple because it's a multitude of feedbacks. It's not just 1 or 2 feedbacks in the system. It can be 5, 6, 7, or even more. But nevertheless, they still work in those dynamics, and then it's always important which one of the feedbacks is strong and which ones are weak. And this is important if we want to intervene to understand what is the structure and where can we influence that behavior. And that's also why Malika in the next section will show us a real case of the Brazil study and explain us how we can use this insight of causal structure to then develop a theory of change.
Thank you, Jean. So I hope all of you have been paying attention to reinforcing loop and balancing loop and delays, because we're going to be exploring that with the Brazil case. And I think most of you are familiar with the Brazil case. Next slide. So we're going to be using an understanding of systems change to theorize a theory of change. Thank you. Next slide, Matthias. So most of us know the classical theory of change. This is a very famous picture, which you probably have used in your theory of change. So theory of change is usually do A plus B plus C and you will get magic, a miracle will happen. So we expect a miracle to happen in our theory of change. We don't really know how that miracle will happen. What we want today is to take you, next slide, to explore with you how we could do a systemic theory of change. So for us, just as a metaphor, a theory of change is not expecting miracles. We're going to give you a course today in miracles. So we're going to make you do miracles by understanding delays, by understanding balancing loop, by understanding reinforcing loop, and all the curves associated with it. So that's our miracle. We will be talking about the Brazil case. I think it's the soy system in Brazil. We started to talk about this case in the last one. I think many of you were there in the last one. So as most of you know, the soy supply chain is largely responsible directly or indirectly as well to deforestation, whether it's in the Amazon or the Cerrado or other parts of Brazil. We will explore different parts of the soy system today to explore systems practice and develop a systemic theory of change. It doesn't mean we will have in this session the definitive systemic theory of change, where we will help you to explore how you could be thinking more systematically about your theory of change. And next slide. So for us, for John and I, when we sat down, when we explored the Brazil case, we think to develop a systemic theory of change, it's very important to map the system behaviors. You can use a range of approach in system thinking. Today we will be using causal loops and links. It's very important that we identify the loop types, the type of feedbacks and the delays. It's exactly how Jean explained, you know, because the loop types and the type of delays will dictate what happens to the behavior, what type of curve you will get in your system, what for different factors. So once you've diagnosed the behavior of your loops, we're going to use something called archetypes to identify what might be future behavior patterns. Because why is future behavior patterns important? Because what you want to do is to change the future. So you want to know what might be the future behavior pattern, and how can we have desirable behavioral patterns in the system. And then last thing, we're going to look a little bit at the human emotions, which is often a manifestation of the system structures. Please feel free to challenge me on this one. But I think having read a lot of social psychology, I think there are distinctive human emotions that reflects different types of system structures. And then lastly, we use those 4 steps to theorize our theory of change, so to move from what we think is undesirable to desirable. So as I spoke, we will use the Brazilian soy system. So next slide. And before we do that, we're just going to talk a bit quickly about system archetypes. Jean, tell me why system archetypes is important for us to know.
Yes. First of all, what are those archetypes? They're basically narratives that explain feedback structures behind certain problematic patterns. It makes it a little bit easier to recognize those patterns and to explain what are the reasons for those and how we can overcome them. And on the right, you see some of the examples: limit to growth, shifting the burden, escalation, eroding goals, strategy of the commons. So you probably heard the words already, and you probably also know the concepts. And it's especially interesting to look at those from a systemic perspective.
Thank you. So we will be exploring 2 archetypes today, and we will explore with you why knowing which archetypes are very important. So we will first start with one archetype. Next slide. So in Brazil, given the big deforestation that's happening, I will start. Matthias, if you can just show the map on the first loop called zero deforestation. So what you get with deforestation is that deforestation in the Amazon, in the Brazil, in the Cerrado, that has created a lot of international pressure. So more deforestation means there's been more international pressure to do something, so plus. So more international pressure means there has been a little bit more buy-in from supply chain actors to do something. And more buy-in from international supply chain actors has led to some deforestation policies. And some deforestation policies has led to a reduction in deforestation. More or less, we don't know how much, but we assume that there is a little negative feedback loop here between zero deforestation policies and deforestation. So now that you know what's a reinforcing loop and what's a balancing loop, Jean, maybe you could do the count. We will ask you to put thumbs up if you think it's a reinforcing loop. So those that don't put thumb up think it's a balancing loop. And Jean, you could make the count of.
Yeah, maybe just one comment who don't know yet with Zoom. There's actually on the bottom you can make reactions, and there you have the option to click on thumbs up, and then we can see it in your pictures directly. So yes, so let me ask you. So the first loop that Malika just explained. Please thumbs up if you think it's a reinforcing loop. Okay, Malika, are you counting?
I see 2 thumbs ups. How many do you see? 3?
I see it's 3, 5, 6, I think I've seen.
Okay. So this is actually a balancing loop. It's a balancing loop because deforestation is leading to all these things, but it's not reinforcing deforestation. It's actually reducing deforestation. So it's actually balancing whatever is happening in other parts of the system that's leading to deforestation. Is actually not reinforcing that pattern. Okay, are we clearer the balancing and the reinforcing loop? Because we are gonna explore the next one. So deforestation, when there is more deforestation, there is more soy supply because we're expanding farms for soy. And the more supply is, the theory is that it should reduce the soy supply demand gap, okay? Because there is a soy supply demand gap. There is a soy demand, and we're gonna soon explore this soy demand. And but because there is this other loop, the soy supply demand gap, the more soy supply demand gap leads to more soy expansion and investment into ecosystems, and the more soy expansion is, the more deforestation there is. This is a bit of a tricky loop, so please thumbs up if you think it's a reinforcing loop. No thumbs up if you think it's a balancing loop. Jean, can you do the count?
Yes, I'm trying. I think I counted 6 or 7 maybe.
For reinforcing loop.
Yeah.
So actually this loop is actually, when we first mapped it, I also thought it was a reinforcing loop. So it's very counterintuitive, but it's actually a balancing loop. Jean, can you tell us a little bit more what makes it a balancing loop?
Yes, if you can go to the next slide, Matthias, then we also have it in there. Exactly, it's basically that this bottom loop, the B2, is satisfying the soy demand. So more deforestation, more soy supply, less gap to the demand, so less soy expansion needed and less deforestation needed. So once we walk through the whole loop, we have like a decrease. Deforestation doesn't increase more and more, but actually it's stabilizing at some point. And if it would be reinforcing, then would kind of lead to more deforestation. Every walk through the loop would lead to more of an outcome. So in this case, they are both balancing.
And thank you, Jean. And next slide. With the next slide, you will see it will become even more clear. So the next slide is a little bit more intuitive. So more soy supply creates more competitive feed, so more affordable feed for industrial meat production, which leads to more meat consumption. More meat consumption leads to more soy demand. More soy demand leads to more soy supply demand gap. Can you thumbs up if you think it's a reinforcing loop? Jean, can you make the count? I think most people think it's a...
I see a lot of thumbs. I would say almost everyone.
Yeah. Unfortunately, the thumbs disappear after 10 seconds. So exactly. So that's a reinforcing loop. And next slide. So what's really interesting in this loop is that usually you would expect that more soy supply would close that soy supply demand gap, isn't it? Because that's a bit the theory of market, the more supply then the less demand. But what we find is that more soy does not reduce the soy demand gap. It doesn't balance this loop. This is because the soy supply is creating its own demand. It's creating its own demand because it's making competitive feed available due to externalities, due to soy being produced quite cheaply due to high environmental externalities. And the more competitive feed there is, the more we can afford to have industrial meat production, because that would not be possible if there were no competitive feed. The more industrial meat production there are, the more we consume meat, the more we transition towards meat, a higher meat diet, and that's all over the world. And that creates its own demand. And that doesn't close the soy demand gap, but actually continues to increase it. So that's why this is a reinforcing loop. And what happens is that this is a balancing loop, but this balancing loop, the zero deforestation balancing loop, does not consider that meat consumption is increasing and that soy with its competitive price is increasing its own ability to produce meat quickly. So deforestation is only acting on soy supply, but is not realizing that soy supply is only its own soy demand is being created. So that's just being reinforced. So so right now deforestation is just acting on the soy supply, but not on the feedback loop that's creating its own soy demand. So next slide. So in addition, there is an additional loop, and this loop is very easy. So so this is a balancing loop in which this loop is trying to reduce deforestation. In this loop, the more deforestation there is, the more international pressure there is. But whereas here there is buy-in from international supply chain, here in this what we call loop R or B, panic clearing. If you could put your mouse here, Matthias. The international pressure is creating more farmers' fear or government fear of future restrictions, and that's leading to even more deforestation. So there is a loop that's opposite to the balancing loop. So you can guess what kind of loop it is, isn't it? So thumbs up for all that think it's a balancing loop. Okay, great not to see any thumbs up. Perfect, you understood the theory. So that's a reinforcing loop. So what you get is that this could be balancing deforestation, but you've created at the same time a reinforcing loop that's reinforcing deforestation. And often this is what we are getting in our policies. We are trying to balance a process here, but in the same process that we've tried to balance a process, we've actually create a reinforcing loop. And just Alexandra, how far behind are we in time or ahead?
So we have 12 minutes to finish this session.
Okay.
The present case.
Okay, thank you. So next slide. So Jean, now tell me, what kind of archetype are we seeing in those 4 loops that we've built for Brazil?
Yeah, thanks for the question. What we're seeing here is actually the shifting the burden archetype. It's also called addiction or dependence. The narrative kind of goes like this, that the implemented intervention only addresses a symptom and not really the underlying issue. And in the worst case, our symptomatic solution worsens the issue or can even prevent a fundamental solution. And on the left, you kind of see the generic structure of this archetype. So we have a problem, and we're implementing a symptomatic solution, which helps in the short term. But for the long term, we would need to work on the fundamental solution, the balancing loop on the bottom. And the main problem is that often our symptomatic solutions might also have unintended consequences that then actually worsen the possibility of implementing a fundamental solution. And the nice thing with archetypes is we can directly relate it to some kind of behavior, what we would expect. So on the right, we can see if we have such a system, if we're trapped in this archetype, then the problem symptom might reduce in the short term, but in the long term, it's continue to grow and to grow. And so in the next slide, if we compare that to our Brazil case, so putting side to side the generic structure with our Brazil case structure, we can see it fits the archetype quite well. So we have the two balancing loop, we have the symptomatic solution, aiming at the supply chain actors, but we also have the fundamental problem in the bottom, which is the soy demand, the ever increasing soy demand. And we also see the unintended consequence on the sides, the panic clearing by farmers. And knowing that we see this archetype here, we can also make assumptions about the future behavior. So if we look at the next slide, so if we only consider this part of the system, which is of course not all, but it's already an important part, we can try to anticipate, okay, if this continues like this, what could we expect to happen in the future? And just based on our structure now, we could imagine that soy demand will continue to increase because of the reinforcing loop that we identified. So the soy supply is trying to close the gap by ever more increasing soy production and soy expansion, which then would also lead to increasing deforestation in the future. And now the big question, Malika, how could we eventually act to change this future behavior?
Yeah, great, Jan. So we've just done some potential speculation. Next one. So when Jan and I built the archetype and look at the possible trends in the future, what we thought is actually really important is actually closing that soy supply demand gap. So that means soy, yeah. So the more the curve of soy supply and soy demand come closer together, the more we are likely to reduce deforestation. So this means that we cannot act on soy supply only, we have to act on soy demand. So this might seem very evident for some of you, but we're just showing you the theory behind, because the theory is important because it depends on where you're going to focus most of your attention. Because right now, if you look at the soy supply chain, most of the focus has been on soy supply, isn't it? The zero deforestation policies only try to act on the soy supply. There has been some effort to reduce soy demand, but when we think of soy and the main policy globally, we think that we would say that it mainly tackling the soy supply. So we think that we know that there's already been some work going on reducing meat consumption, but we think that some potential focus for attention would be on reducing that gap between soy demand and soy supply. So this is not to tell farmers that we want to take away their livelihood, but we just want to make that soy demand and soy supply, that gap close. And we think this is more likely to reduce deforestation. And then there could be other sub-interventions that would make sense based on those loops. These are potential interventions. This is, for example, increasing crop productivity, so increasing soy supply, so that it doesn't depend on deforestation, on soy expansion. But we know that there are limits to that, to how much you can increase crop productivity. But as well, if this loop is real, that zero deforestation policies are being matched, that balancing loop is being matched by a reinforcing loop, reinforcing deforestation, there is need to reconsider how we're doing zero deforestation policies. So that is shifting the burden for you. So if you have any question on that please type it in the chat box. Unfortunately, we're a bit limited in time, but we definitely will consider your questions and probably try to bring them forward in the third or at the end of this session. So I just give you 30 seconds. If you have any questions, please type it in the chat box, because after that we will go to a different archetype. So next slide, Matthias. So we've looked a bit at the global system now, but let's go into one part of the system, what deforestation is doing in Brazil. So what we see from the evidence, from the scientific evidence, is that the more deforestation there is, the less water evaporation storage there is. So it's a negative feedback loop. But the more so more deforestation is less evaporation. Less evaporation is less rainfall, or more evaporation is more rainfall. But in this case, less rain for the crops is less evaporation, less rainfall. That's why plus plus. And then less rainfall is less crop productivity. And then, but this moves in opposite direction, interestingly. So you would think when your crop productivity reduces, you will not expand into soil, but actually the opposite happens. That's why negative means these two move in opposite direction. So again, is this loop a reinforcing loop or a balancing loop? Less rain for crops. So if you think it's a reinforcing loop, please put your thumbs up. And again, it's a bit of a tricky loop to know, to follow. How many thumbs up for reinforcing? What did I say? Thumbs up for reinforcing loop? Yeah. John, can you do the count quickly? Or did we meet?
I saw 4 thumbs, 4 or 5 thumbs.
Okay, so the 4 who put, or the 4 or 5 who put their thumbs up, you're actually right. It's a reinforcing loop. Let me explain why. This is because this loop is not reducing deforestation, it's reinforcing deforestation. Next one, let me explain why. So deforestation leads to less rain, but more soil investment. So it's actually leading to more deforestation. This is because as there is a decrease in crop productivity, only one soy season instead of 2, farmers tend to invest more in irrigation or more into crop area. So basically they reinforce this deforestation. So you would expect actually, because they are so impacted, that reduces deforestation, but actually it reinforces deforestation. So that's why it's so important to understand, is it a balancing loop or this is a reinforcing loop? This is a very wicked is a very wicked loop, because already they are impacted, but they reinforce this pattern. And so next slide. So then what, so let's look at the relationship, this loop called loop less water for everyone. So what happens? So the more water there is, the more soil supply there is, because whether it's from rainfall water or whether it's from irrigation water, that makes sense for any crops, isn't it? And then but the more soil supply there is, the less water there is for the farmers. So please let me know if it's a reinforcing or a balancing loop. I see some question from Liz. So what's the loop that reinforces the behavior of the farmer? Okay, for which one you mean? Less rain for the crops or the water one, Liz? Okay, so you mean for the less rain. So what's the behavior of the farmer? So basically they start depending to adapt themselves to less rainfall. They actually start clearing more land for soy to increase their profitability. or they start depending more on irrigation. So that's why it's called soil expansion or an investment. So the behavior is an adaptation. It's actually a climate change adaptation behavior. So because they are affected by less rainfall, they need to compensate that loss in productivity, and what they do is to clear more or depend more on irrigation. So that's kind of a short-term adaptation behavior. So I didn't see what were the thumbs up, but the next one. So it's a balancing loop, because on one side it's plus, and then on the next one, the more soil supply, the less water, the less soil supply. And then let's look about the effect of delay. So next slide. So in systems dynamics and system theory, when you see this little bar here, that looks like a bridge, Matthias, could you put your mouse on this? Exactly. This means there is a delay. So we know there is a delay between deforestation and water availability, because deforestation reduces, the more deforestation there is, the less water evaporation and storage there is. But before that starts affecting water availability, there is a delay, and we don't know how long this delay is. It could be 10 years, 15 years. It's a bit the same as the delay in climate change between cause and effect. You know, that delay is sometimes unpredictable, uncertain, it's very difficult to predict it, but delay matter a lot for the system, as Jan has pointed out. So what happens is that there is a delay in water availability, but when this delay comes into effect, this will affect this loop. There will be less water for the farmer, and the less water there is for the farmer, the less soil supply there is. So this whole thing, this is a balancing loop, and this whole thing is also another loop. And I will just say again, this is another balancing loop, because when this comes into effect, deforestation will lead to long-term decrease in water availability, and hence will negatively affect the soil supply. So this will not be, deforestation will not reinforce soil supply, rather there will be a collapse. So this is a very easy archetype. Jean, can you tell us what the archetype is and why does it matter to know?
Yes, next slide, please. So this archetype is called limits to growth. And it basically says that nothing can grow forever. There's no unrestricted growth, and there's always some kind of limit that will eventually push back. And in the worst case, the growth is even going to destroy its own carrying capacity. So remember the example that I showed you with the population growth and the pollution destroying its own food supplies. This is exactly the case for the limits to growth. So we have some kind of result which might grow exponentially, reinforces itself, but with a long time delay, we are destroying the limiting condition and the carrying capacity. And as we said before, it depends a little bit on the delay, what behavior we might expect. If it's like kind of a smooth S-shaped growth, or if it might lead to a collapse of the system. So if we look on the next slides and again compare the generic one with the one that Malika presented, so we can see that we have in the Brazil case even two reinforcing loops. So we have this increasing meat consumption loop at the bottom, and we have the less rain for the crops that kind of pushes farmers to increase their available land. So those two are pushing for more and more deforestation, for more and more soil supply. We have the slowing action, which is the B1 loop, that there is less water for every farmer as they increase their supply. But most importantly, we have this big balancing loop, B2, that over time the deforestation leads to less water availability, less water per farmer, less soil supply, and that eventually, as we can see on the next slide, the system could collapse. So if we now kind of again look into the future just with this structure, and this might be something that we could expect. So if we continue with deforestation, water storage is going to continuously decrease. And while soil supply might be still increasing in the beginning, at some point water availability will decrease as soon as the delay is covered, and if it's kind of hitting the system, and then it might lead that also the soil supply doesn't have the necessary water supplies anymore, and the system could collapse. So what can we do against it, Malika?
Okay, great. Next slide, Matthias. So this is just an example to show you that actually, because one of the limits to growth could be water, which is related to forest, but it actually what matters for the farmers is actually water. I mean that what really is the limiting factor in the system is actually more water than forest, but of course water is related to forest. What we would want in the future, a desirable change, is we're not looking to reduce that soil supply. We're actually looking at maintaining the water supply and maintaining the soil supply. So we don't. So if we look at a system behavior, we're looking at just managing water supply and soil supply, and that's good news for the farmers because we're not trying to affect their livelihood. We're just telling them if you manage to maintain that water supply, then you will be able to manage your water supply. And that to manage that water supply, you will need to increase your water evaporation and storage capacity. And where is that possible? Of course, through not reducing deforestation. So some of the intervention that we see is actually more awareness of that water cycle. Rather than focusing on to farmers to reduce their soil supply, more focus on supporting a sustainable soil supply chain in terms of not causing damage to your water supply. And again, we see if we see an adaptation where you're getting an adaptation cycle in climate change adaptation that's reinforcing deforestation, find ways to increase crop productivity so they don't have to rely more on deforestation to increase their crop profitability and productivity. So this is, as we say, a potential theory of change. Like we're looking at the system. And the next slide. I saw that Lee said, I hope we will be getting to the financial sector. This is absolutely right. So this is a qualitative model that I work with the GGP team in Panama and in Brazil. Pascal Assis is here. Aline will be very familiar with that. So right now we've just shown you a little part of the system. So this is on the right top corner on the water cycle here, and then we've shown you, yeah, exactly, Matthias, just here. And then we've shown you another part, which is and then on the bottom corner, which is the zero deforestation policy. So we've explored cause and effect and delays in this part of the system. So we haven't shown you the cycle between land value and land grabbing. We haven't shown you the financial sector and how that's reinforcing soil expansion. We haven't shown you how this is a national policies for soil as a model of development is being reinforced. So we haven't shown you every part of the system, but what we are saying is very important to understand how the system works, the system structure and the system behavior, and theorize about different theory of change in different part of the system before you actually decide on what would be your theory of change. So it's very important to understand the whole system and then go into the behavior in the system before you decide on what's going to be your course of action. So that's what we call a systemic theory of change. This is when you understand really your system structure, your system's behavior, and you're theorizing what would make more sense in terms of causal loop. So you're not getting linear theory of change in which you will create magic. You're really looking at what are the loops in the system. How are you part of those loops as well? Because all change agents are also part of this system, and to understand how to act based on the system behavior. So we're going to go straight into the next slide, which is leading through complexity. Thank you. So, and next slide. So, this stream falls under Liz Melvin, which is multi-stakeholder collaboration. And it's very important. Since the beginning, we have really reinforced how system thinking and collective leadership is actually two tools that needs to come together for multi-stakeholder dialogue. And we will show you a little bit why this is important. So in general, when you see when you get certain type of system structure, as we explained, you get certain systems behavior. And there are also human emotions manifested in different types of systems behavior. We tend to often judge, like if we see escalation between different stakeholders, or if we see stakeholders in denial of certain patterns, we actually judge it. But actually, if you understand that this is often a manifestation of a system structure and the behavior, you tend to judge it less, but to see how do we work with the fact that this type of structure often leads to certain human behavior. The classical one is escalation. And this is an archetype that we didn't show you today, but often escalation, as you can imagine, leads to tension, anger, blaming. And if we had shown you that escalation archetype, you would have seen it very clearly. But today we explore limits to growth. And often limits to growth, there is ignorance and denial that there will be a limit to growth when the delay comes into effect. For those that understand that the delays come into effect, there is a lot of anxiety. Similarly, with the shifting of the burden, if we're only addressing the symptom, not the underlying issue, there is probably a lot of confusion and mistrust among stakeholders. And probably they see it as, they perceive how change makers are acting as unfair on the system. If you come from Brazil, you will be very familiar with this sense of perceived unfairness that farmers are experiencing right now. And this can lead to anger and growing resentment. The same thing with delays. A lot of research in social psychology shows the reason why it's so difficult to tackle climate change is because the risks are into the future. And the risks are, like it's a question of scale. It might not impact you, but the next country or the next vulnerable place plus is going to happen in the future. So delay often create a lot of uncertainty, and we know that uncertainty leads to a lot of powerlessness. And when we are powerless, we probably tend to discount future risk. We probably act on short-term goals. So when we see that there are certain human emotions associated with the system structure and the behavior, we shift away from judging it, but to see, okay, this is actually often, this is how, like we often respond to, our human reaction is often the case with a type of situation. Then we see how do we work with those human emotions rather than oppose them. So next slide. So the reason why we chose this picture, because a systemic theory of change works intelligently with the system structure and behaviors. So that's system thinking, the open mind, and related emotions. Because if you're going to be a collective leader dealing with multi-stakeholder, you're going to need to work a lot with human emotions, and you need to see that it's a manifestation of what's happening in the system rather than coming out of the blues. So you're going to have to work with both of these, because both of these are the manifestation of the system. Next slide. So we need to attend to the structure, the systems behavior, and the related human emotions. And this is a little bit where we want to bring you closer today. So you need to actually, as collective leader leading those multi-stakeholder dialogues, understand the system, understand the behaviors, and understand the associated human emotions. And next slide. So we have the question for you. How are we with time, Alexandra, before the corona example?
We have 16 minutes left for the end of the workshop.
Okay. Jean, should we give 2 minutes to reflect on this question?
Yeah, that sounds good.
And so based on what you've heard so far, take 2 minutes quietly, take a big breath before to just think, how would a multi-stakeholder collaboration work more intelligently with the system archetype we've just presented to you and the related emotions in the Brazil case? So what would you do if now that you've understand some of the systems archetype and the human, the related emotions, how would you differently to what has been done in Brazil? And Sandra will type this question in Spanish. Please feel free to also answer it in Spanish. We won't have time to deliberate on each of your answer, but we would really like to collect your feedback because how you think about it is very important. So please, we will be collecting what you write in the chat box. So I just start, we will just have 2 minutes in silence. Thank you. Starting now. So we will soon transition to the last part of the session. We will do a game simulation on COVID. If something comes during the simulation or later on, please keep on writing your answer in the chat box because we really look forward, as we mentioned, to really hear from you. Over to you, Jean.
Thank you, Malika. If we can go to the next slide, Matthias. So as Malika said, now we want to make like a short exploration into the world of quantitative modeling and play a little simulation game. And I very like this graphic to kind of show a little bit why quantitative modeling. So when we do systems inquiry, it might be we feel like the person, that we find connections, that we feel enlightened, that we see more and more causal structure. But in some cases, it can also be overwhelming. And especially if we want to include a lot of detail, that then everything is connected and we can't see the clear picture and we find ourselves in the same position as in the beginning. And therefore it's, so first of all, very important, not focus on too many details, but really on the important parts when doing a systems analysis. And second, you can use computer simulations to help you still see the main patterns within your analysis. And that's what we want to do for COVID. If you can go to the next slide, Matthias. So just briefly, this quantitative modeling especially comes from a field called system dynamics. And that's also kind of the father of the whole field of system thinking. If you think of Peter Senge and Donella Meadows and so on, and this whole MIT group, they all studied system dynamics. And it allows us with the quantitative modeling to simulate the dynamics based on our assumptions that we have, to also validate our assumptions with data, and to test interventions under various scenarios. And on the next slide, we would like to do that today in a very simple example on COVID. So on the right, we've already talked about kind of the two main feedback loops, this reinforcing loop of the infection spreads and the balancing loop. And now we want to see a little bit how might policies affect those two loops. So what we want to do is support a fictional region to understand the COVID dynamics and to compare policy alternatives. Imagine we are at the very beginning of the epidemic and we first only focus on the health goals. So we want a low number of deaths, low number of infected, and we want to buy some time that we can think of other policies and gather data. And policy suggestions, there has been 3 so far. 1, free movement for all, so basically no restrictions. Second, we isolate the infected, so we have a quarantine. And a third would be social distancing. And on the next slide, we see the assumptions of the model. So no model is perfect. No model is a perfect representation of reality, but some are useful. So the saying goes. And these are some of the assumptions that we have now in the model. So the community has a population of 100,000 people. Our hospital can take care of 100,000 people in intensive care. And our public health capacity can take care of 1,000 people. So to monitor them and take care of them remotely. And we have on the right the virus data. So we assume a reproduction rate of 2.5, an average incubation time of 5 days, an average infection duration of 10 days. We think that there's 10% of patients who have a serious infection and they need to be hospitalized. And the fertility rates ranges between 1% and 4% based on the level of healthcare the patients receive. And other assumptions are we start the simulation with the import of 3 infected cases into the region. We assume very positively that we can rapidly identify infected people. And we also assume that we are immune after we went through the infection. So the next slide, please. So, question to you, very briefly, just based on the information that you had and maybe some ideas. What do you think would be the best suited policy? And in this case, just from a health perspective, so not a social, economic, or environmental perspective, just based on those 3 goals. So you can make your votes now. Matthias, you will tell us as soon as we have all the votes. Great, the votes are in. I think you see them all. So free movement, not many people believe in that. Isolation, 41%. Social distancing is the most popular vote. So great. Let's see if the model can confirm our ideas and assumptions. So if we go to the next slide. I don't want to go too deep into the model structure, but just to give you a general idea how this works. So the notation is just a little bit different than the system maps we showed you. Mainly we talk here about stock and flows. So imagine all the people in the beginning are in the susceptible stock, 100,000, and then some of them get infected, so they move from the susceptible stock to the exposed stock. Then they're advancing after the incubation time. That means they are in the infected stock, and then they might be dying or recovering and moving to the respective stocks. So kind of they flow through the system. And on the next slide, we see the different factors that are impacting those flows. So if people are infected, if they're advancing, and if they might be dying. And R1 is this reinforcing loop that we looked at earlier. So the more infected people we have, the more contact with infected people, the more susceptible people are infected, and the more infected people we have. And B1 and B2, these are also the loops that you know already. This basically means the less susceptible people we have within the stock, the less contact we have, and also the less contact density. So the less infections we have over time. So these are the 2 loops that you already know. And there is another loop, B3, which is very important. So we assume that 10% of the infected cases are serious, so they need hospital support. This puts a strain on our hospital capacity, as we can only handle 100 people. And this then influences the fatality rate and determines how many people might be dying because of the infection. And so let's now explore what the simulation shows us. And first, for the free movement for all policy on the next slide. So maybe some of you have already seen kind of these curves in relation to COVID. This is kind of the general behavior. So we see different graphs and how they develop over 360 days on the x-axis. So we look at 1 year here. And we can see the gray graph is the susceptible people. It reduces as more and more people get infected, which is the blue graph on the bottom. But at the same time, people also recover. Like after the 10 days of infection time, they also recover and then are immune. And so we can see that, yeah, kind of 30,000 people are never infected after 360 days, and around 70,000 people were infected. Most of them recovered healthy, but some of them also died, as we can see on the red line on the bottom. Let's zoom in now a little bit and check the important graphs. If we go on the next slide. So here we have on the left the total infected people. So we see it increases rapidly and we reach 70,000 total infected. And on the right side, we can see the actual problem. At the peak, we have almost 1,000 serious cases that need hospital care, although our hospital capacity is only at 100. So it's 10 times higher than our hospital capacity. So to kind of assess this policy, we have to say we have a high number of deaths, a high number of infected, and also almost no time to react with the reinforcing growth, so it doesn't fulfill our expectations. So let's check the next policy, which is the isolation. So we implement a 40% isolation policy. That means we're trying to identify and monitor at least 40% of the infected people and put them in quarantine. And on the next slide, we can see how this goes. It's actually interesting. So we see the blue line is now the isolation policy compared to the policy from before. And we can see in the end, we actually also almost reached 70,000 infected people. And also when we look at the serious cases, we almost have 900 serious cases at the peak at around day 240. So also 9 times more than our hospital capacity. And we can also see in the number of deaths, it's also still quite high, very close to 4% on average. So we have a high number of deaths, high number of infected people, but we can see we can buy some time. So we have a little bit more time to react and to eventually think about other policies. And then to the third policy. Yes, that was, okay, now let's go to the third policy. So there we have now the social distancing at 50%. So we assume we can reduce the social contact of every person in the region by 50%. So let's look at the results. Let me simulate that. And yes, we can see we actually reduce it a lot. So on the left, we can see the green line. It stays at around 10,000 infected people throughout the 1 year. And also on the right line, now we can see that we always stay within the hospital capacity. So we don't over stress it. And also the number of deaths is much lower than in the other 2 policies. But on the next slide, we see that this would need to be in place for a long, long time. So here now we see the simulation for 2 years, 720 days, and actually we would need to implement this policy, social distancing, for 2 years. If we stop before, it might just increase reinforcingly again, and we would have the same situation as before. And this, of course, also then can have large impacts on social and economic aspects of life. All right, I still had some slides for the COVID case, but I think we should slowly wrap up as time is running. So to the next slide. Just very quickly, we could also, of course, test what are the synergies between policies. I don't want to go into the graph, but there we can also see, okay, what happens if we combine isolation and social distancing, and actually it would have much beneficial effects on the system. And on the next slide, there's a short summary of what we can kind of see from this little game. We will send the slides to you so you can also go through them. It's basically combining policies would actually be best to reach the goals, but obviously it would also be interesting to test some additional scenarios. What happens if the virus comes back? What happens if we might not have a vaccination? What happens if not everyone is immune and might become susceptible again? And so on. And of course, also the long-term impacts on the environment, the social life, and the economy. But with all of that, quantitative modeling can help us to kind of handle this vast amount of information. All right, this to our little COVID simulation game. And then I hand over to Malika for a short wrap up and an outlook for the next session.
Hi, welcome back. We are doing a re-recording of the last piece of the session, which is the summary takeaways, because we had to rush it a little bit the last time. So thank you for being with us again. And so, Jan, could you tell us why complex systems cannot be predicted and how do we find patterns in systems?
Yes, thank you. That's exactly what we looked at the beginning. So we saw that we mostly can't predict what's happening in the world exactly, but we can always see certain patterns and trying to explain them. So we played this little paper fold game as an example how quickly exponential growth is developing, and also to try to identify what is the structure behind this exponential growth. So that's when we looked at feedback loops. So the reinforcing feedback loops that kind of reinforce their initial behavior, and also the balancing feedback loops that kind of stabilize the system over time. And with reinforcing feedback loops, we have some examples given. There were also some very interesting examples that you gave in the chat box for those reinforcing loops. One example was the advertising of companies, which is a very well-known loop, also kind of described as the engine of growth, where we see a certain sales, which leads to profits. Those profits are invested in more marketing. More marketing means more customers, more profit, and so on. So this is kind of the marketing loop. We also had other examples that you gave us. Fake news, also a very interesting topic where we can see reinforcing feedbacks. There it's especially that with more fake news, traditional news sources lose their credibility. And that means this invites even more people to publish news with relatively weak sources. So it kind of also reinforces the creation of fake news. And another interesting case was also the extinction of animals, which is also mostly based on the introduction of invasive species, which repopulate themselves exponentially because the balancing loops are missing that keep them in play. And so that's how they grow exponentially and replace the traditional animals in a certain place. So that's also very important what we looked at, that nothing can grow forever. There are balancing loops, but it's really important how long does it take until those balancing loops actually impact the system behavior. And one example there was the limits to growth archetype, so that there is always a limit, but it's very important to look at the delays, which can change the whole system behavior. And also one of you commented the climate change, if this is also a limits to growth archetype, and that is exactly true. It's actually a limits to growth archetype with very long delays. So we're producing CO2 emissions now, but we're only expecting to see the biggest impacts in maybe 30 or 40 years. And this is especially worrisome because once we see the impacts of climate change, it's too late to change our behavior, or it won't have the impact any longer. So that's why it's extremely important if we see patterns, we need to understand, okay, what are the feedback loops in the system? What are the delays? And do we see certain archetypes so that we can understand the past behavior patterns and plan interventions accordingly? And for that, actually, Malika showed us in the Brazil case how we can use such maps for planning future interventions.
Thanks, Jan. I found it very interesting what you mentioned about, when balancing loops come into the system. When you introduce something new into the system, when will the balancing loop taken into effect? So this is exactly what we discussed in the Brazil case. We showed you some interventions and what kind of loops are feeding into the system. For example, we had a reinforcing loops on zero deforestation, in which zero deforestation loops were making farmers deforest more into the future because they were worried what kind of future policies would be. That was a reinforcing loop. And at the same time, there was a balancing loop because zero deforestation was leading to certain supply chain actors taking, monitoring where the soil was coming in and reducing deforestation in that way. There was a question from Safia, I think, about whether we were showing in that loop zero deforestation and net deforestation. Just for those that don't know the difference, zero deforestation is about preventing deforestation, whereas zero net deforestation is about, it's the balance of forests that exists. So in this case, in zero net deforestation, we could be deforesting, but we could be replanting, and it's the forest balance that we will be measuring as part of these policies. So if we had introduced net zero deforestation loop in our example, we wouldn't be focusing as a factor on deforestation, but rather the amount of forest. So that's why the loop that we built is a zero deforestation loop, because we are showing deforestation. So what I'm trying to say is that the factor that you will see in the loop would reflect what's important for those policies. So in this case, we showed you how in Brazil, looking at certain archetypes, we look at two archetypes. We showed you how zero deforestation was part of a loop that was shifting the burden. So it was not tackling on the main issue, which was the increasing soy demand, but rather it was tackling on soy issue. And that was creating other loops, other balancing loop, but also other reinforcing loop. And then we also showed you an example of limits to growth in the Brazil system. And by understanding these archetypes, we were explaining to you how you would be better able to see what are the patterns in the system and what are the better places of intervention, because you are understanding what are the patterns, what are the behaviors of the system. And then lastly, I talked to you about often the human emotions that you see in a system don't come out of nowhere. They are not irrational in a way. They are actually a reflection of the system structures and the behaviors, of course, also of human psychology. So what is very important for us is that you see that if we are going to work on multi-stakeholder dialogue, we need to both understand, we need a joint approach from collective leadership and system thinking to address system structure, systems behavior, and emotions. And then you gave us some example when we asked you what, once you saw this example from Brazil, we asked you what kind of interventions or what kind of approach might you see in Brazil. So I'll just summarize some of the responses. So Pascal Bonzam told us perhaps it would be good to use role-playing games to feel the emotions better. We totally agree with you that we need to understand what game playing and role-playing game shows is to show you the system's behavior and the emotions manifested. So once people see that actually in any system, if you have that kind of behavior, you will see that kind of emotions. You start seeing it as a pattern and manifestation of the pattern. So the more you are able to see that structure, that behavior, the more you are able to really tackle it rather than to judge it, for sure. Anga Pratanama, if I'm saying the name correctly, told us would incentive schemes for implementation work? And that my response would be when people talk about incentives for implementation, people often think about financial implementation. So I think it would be important using systems thinking to see, actually, are we talking about financial implementation when we see those loops, or are there other type of incentives that is becoming apparent? For example, if we didn't show it, but if you had looked at the escalation archetype, you would see in Brazil that farmers have been excluded. And that's creating an escalation between farmers and change agents. So actually, some of the incentives could be inclusion, being heard, allowed to lead on sustainability. So we should think more broadly about incentives by looking at the system structures and behaviors. And then lastly, Jim Whitestone gave an example of understanding stakeholders' objectives and looking for trade-offs. Totally agree with you. What system thinking brings is to give you a better structure to see what those objectives would change in the system. So that's how you can bring the perspective of the stakeholders. What do they want? And then to understand trade-offs, you really need a system map, because you will see if they bring in the objectives, how will they change the system? What kind of trade-off in other loops would you have? Are the objectives trying to balance a loop, or are they trying to reinforce something in the system? So you will be really able to understand what kind of loops, if you introduce a certain objective, what kind of effects will you have in the loops. And often when we think of objectives, we don't see the feedback that it will have in the systems. So system thinking allows us to see those feedback, to theorize what would be the effect in the system. And Jean, tell us a little bit about the Corona example that you made us played.
Yes, thank you. Yeah, and finally we had a little excursion into a small simulation game with the COVID. It basically showed that sometimes the system analysis can itself become quite complex, especially if we add a high level of detail and also want to integrate data evidence. And then computer simulations can help us to look at different scenarios, to make sense of all this amount of information, and to actually test policies. And those computer simulations are not meant to predict anything, concrete numbers at concrete times, but it's again to understand what are the patterns, and based on our assumptions, what might the patterns in the future look like, and how could we with interventions change those patterns. And in the COVID case, so we looked at those 3 different policies, and we actually saw that social distancing seemed to be most promising to change the patterns in a positive way, although it also has consequences, eventually unintended consequences, that we need to consider. For example, the length of the lockdown would be interesting to also then see what might be impact on the wider system. And yeah, that's what we can use computer simulations for. So this was like a short summary of the takeaways of our last workshop. And so what we did today was, you see it here, diving into systems practice. So this was the 2nd workshop of our 3 workshop series. And we also know that today was a lot of input, was a lot of descriptions of system thinking and systems practice and how it connects to collective leadership. Although it was much, it was really the main concepts of system thinking. So if you understand and if you kind of let it sink, these are really the fundamentals of every systemic approach that you can use for your project work. And yeah, based on the theoretical foundations, in the next workshop, we actually want to apply these. So we then also want to introduce you to some of the methods and tools that you can actually apply them to topics that you are working on right now and want to make it a little bit more hands-on. We will again, of course, send a reminder and send an invite for our third workshop. And then finally, just to say thank you during the session and now also in the recording for your attention. If you have any other questions, comments, feedbacks, or if you want to just talk about systems, please feel free to reach out to Malika or to me. And yeah, we're looking forward to see you in the next workshop, and everything you do, please mind the feedback. Thank you.
I like that, mind the feedback. So we're just to reinstate, we are really looking forward to build a system understanding with you in the third session. And we look forward to see many of you there with real case example from the field that you work. So thank you. Goodbye.